Well, thank you for hosting me. And there's an interesting development. I had a very interesting discussion after last meeting. So the title I had was Top-Down Causation, What is its nature, why can it happen? But after a discussion yesterday, a modification, thanks to Douglas Campbell, maybe we need to use the word top-down realisation. What is its nature? Why can it happen? And I will talk about that towards the end of this talk. So the occurrence of top-down causation, just to remind you, it's the key to evolution where adaptive selection takes place. It's the key to physiology, for example, the heart, and development in epigenetics. In the brain, it underlies all brain functions, vision, learning, reading, and the relation to society, where there's a whole subject of social neuroscience, which is a very active area at the moment. In computers, it enables software to control the flow of electrons in the bottom gates, and this is enabled by the underlying physics. And in physics, I haven't talked about all of these. It occurs determining the arrow of time, which I'll talk about on Friday. It occurs in nucleosynthesis in the early universe. It occurs in superconductivity, in state vector preparation, and in quantum measurement contexts. We could talk about those. Now, the question is, room at the bottom. If physical laws underlie all, how can there be causal room at the bottom, enabling this to take place? The previous talk I aimed to explain the concept and how it works in many contexts, giving sufficient examples to hopefully convince you it does indeed work and has to be taken seriously. And in this talk, I'm going to characterize 5 different types of top-down causation. I'm going to relate it to Aristotle's kinds of cause. I'm going to deal with causal closure of physics at the bottom, and then supervenience of higher levels on the lower levels. So, the first thing, complexity and structure. True complexity, with the emergence of high levels of order and meaning, always occurs in modular and hierarchical structures, because this is the only viable way of building up real complexity on the basis of a set of simple components. And I did mention this last time. I just want to say a bit more about it now. So the hierarchy, with many layers of structure built upon each other, represent different levels of abstraction, each built upon the other, and each level understandable by itself. So if you're a motor mechanic, you don't have to know about quantum physics. If you're a surgeon operating on the brain, you don't need to know a lot also about elementary particle physics. There will be different description and vocabulary suitable at each level of the hierarchy related to the effective entities, and so at each level a different description, even a different vocabulary. It's composed of modules that are quasi-autonomous. They are combined in specific ways to form the structure. The structure creates new possibilities. Oh, sorry, I've said all of this. I'm going to go to the next one here. So this is the physical hierarchy, and I didn't talk about this one last time. Particle physics, atomic physics, physical chemistry, material science, geology, planetary science, astronomy, cosmology. This one here, the life sciences one, particle physics, atomic physics, chemistry, those are the same. It then changes to biochemistry, cell biology, neurology, botany, zoology, physiology, psychology, and sociology, economics, politics. The top levels are very, very different on this side than the other side, because on this side it is thoughts and intentions and purposes which determine what happens at the lower level. And so it changes from a physical hierarchy to being a causal hierarchy in that sense. Now, the key to handling complexity is hierarchical information structure and analysis and associated physicals. Structuring a hierarchy represents a decomposition of the problem into constituent parts and into processes to handle those constituent parts, each requiring less data and processing and more restricted operations than the problem as a whole. So in the hierarchy and in the modules, you're breaking the big problem up into little problems, and then you construct modules to handle the little problems, and then you assemble them into something which will handle the big problems. The levels of a hierarchy represent different levels of abstraction, each built upon the other, and understand it by itself. We find separate parts that act as independent agents, each of which exhibits some fairly complex behavior, and each of which contributes to many high-level functions. Only through the mutual cooperation of meaningful collections of these agents do we see the higher-level functionality of an organism. This is emergent behavior. The behavior of the whole is greater than the sum of its parts, and cannot even be described in terms of the language that applies to the parts. famous article by Phil Anderson called More is Different. Now, intracomponent linkages are generally stronger than intercomponent linkages. So within a module, the linkages are much stronger than between the modules. This fact has the effect of separating the high-frequency dynamics involving the internal structure from the low-frequency dynamics involving interactions amongst the components. So, for instance, in your digital computer, things are taking place cycling at 25 million cycles a second at the bottom level, but you still sit and wait while it loads up at the top level. So it's much, much faster in the small components than in the large ones. In the brain, things are taking place on microsecond level within the brain, but you think at sort of second levels. Deep emergence takes place when the parts can no longer function on their own, which I will talk about later. Abstraction, unable to master the entirety of a complex object, we choose to ignore its inessential details, dealing instead with generalized, idealized model of the object. And abstraction denotes the essential characteristics of an object that distinguishes it from all other objects. It focuses on the outside view of the object and so serves to separate its essential behavior from its implementation. It emphasizes some of the system's details or properties while suppressing others. Information has to be thrown away by the billion bits all the time because the alternatives cannot be examined. So we've got cells in our bodies. If we had to know about all the details that is happening inside each cell, we couldn't even begin to handle the flow of data that would be needed. We have to handle each cell as an object where we don't worry about the internal processes. We just need to know what goes in and what goes out in order to handle how the cell behaves. And so you throw away all the information about the internal processes and just deal with it as a black box with certain behaviors as a black box. And the key feature is that compound objects can be named and treated as units by appropriate labeling. So when you stick a lot of cells together to get let's say a lung, you can now talk about the lung and talk about the behavior of the lung. And so you can deal with these different level of abstractions, the atoms, the molecules, the cell, and the lung. Give them each a name, and then you can deal with the behavior of it at each of those levels. And this happens also, I should emphasize here, this business of building up complexity this way applies to physical systems, and it also applies to abstract systems like language, computer languages, and so on. So the key feature there, and it's one of the things that allows language to function, is compound objects can be named and treated as units by appropriate labeling. This leads to the power of abstract symbolism, recursion, and symbolic computation in mathematics, computer science, and language. What takes place is encapsulation and information hiding. Consumers of services only specify what is to be done, leaving it to the object to decide how to do it. This is an aspect of decentralized control, and it's very, very clear in computer systems where you write modules which will do work subroutines. You send information to the subroutine, you get it back, and you don't care how the subroutine does it. So encapsulation is when the internal workings are hidden from the outside, so its procedures can be treated as black box abstractions. No part of any complex system should depend on the details of any other part. And I'm sorry, this is rather repetitive, involves this information hiding. So this is another description of the cellular compartmentalization is an effective way to build gene circuits capable of handling logical operations in which binary inputs are converted into binary outputs according to user-defined rules. It conceals the implementation of each encapsulated logic gate, which can be individually designed and optimized. To assemble a complex multicellular circuit, one need only be concerned with the input-out function of each cellular gate and the output-input matching between layers. The same variable can assume different roles in different subroutines without mutual dependency, thus lowering the demand for variable diversity. And so you've got your hierarchy in biology, you've got it in computers, and what I want to emphasize, which I didn't properly emphasize last time, is there are orthogonal hierarchy systems in the computer. There's the implementation hierarchy, which I will call the vertical hierarchy, and there's the logical hierarchy, which I will call the horizontal hierarchy. And Tannenbaum writes about the one, and Booch about the other. And the logic of the implementation the logic of the horizontal, the logical hierarchy, it should say latter, the logic of the latter gets rewritten at each level of the former by compilers or interpreters. Downward realization, or instantiation of the higher level code and logic chains down. So you've got logic at a certain level and it chains down to the lower levels, and we'll look at that a bit more in a minute. Causation at each level is in terms of the language and syntax at that level. So what you've got, this is the hardware hierarchy, the implementation hierarchy we've already talked about. And this is the software hierarchy, but this is the implementation hierarchy, and this is this works for any which we discussed last time, your application programs, assembly language, operating systems. But this is still implementation hierarchy, and what happens here is that you put in a logical problem you want to handle, and the example I will use is analyzing aerial photographs to see what is in the photograph, and you put that in at the top, and it then chains down, and that problem, the logic of that problem, gets rewritten at each of these levels. So exactly the same logic which you put in at the top, for instance, as I say, looking at analyzing a photograph to understand what you're seeing in the photograph in an aerial photograph. You analyze that and you write a program in, let's say, Fortran at the top level that will do all the logic involved in that process of recognizing what's happening, a pattern recognition program, and then it changes down until it's happening down at the lower level. So the logical hierarchy gets rewritten at each level by terms of compilers or interpreters. So this is the logical hierarchy. This is what we're going to write in terms of a Fortran program, a hierarchical contextual model for aerial imaging parsing. And this has got a hierarchy in it because you've got a scene, you've got groups in the scene, you've got objects in the scene. Each of the objects is made of primitive features. So there's a hierarchical structure in the logic of understanding an aerial photograph. Okay? To handle the structural variation in aerial images, we model scenes as a group of objects such as cars aligned in rows or roofs clustered in city blocks. And we present, in this paper, they present an algorithm to automatically add statistical constraints to the hierarchy in a minimax entropy framework. So there's a logic there, and that logic, as I've said, that's what you write in Fortran at the top level. Then the compiler takes that logic down to the next level, next level, next level, next level, next level, and eventually you've got it in binary code, and then at the device level, it results in flow of electrons through transistors. So what I'm trying to emphasize here is at each level there's a horizontal hierarchy, and the language in which it's written is different at each of these levels. And that's really a fascinating thing, that exactly the same logical structure can be written in terms of different kinds of logical relationships at each of these levels. So if you've got that at the top level in Fortran, there's one set of rule that applies. Take it down to a Java virtual machine, there's a different set of rules that applies. Take it down to the microarchitecture level, you've got your chip instruction set, it's another different set of rules, but they all have got the same underlying abstract causal pattern that you're analyzing. So like all truly complex systems, again, ordinary language has a modular hierarchical structure. The text, sections, chapters, paragraphs, sentences, phrases, words, phonemes, and letters. Each higher level provides the context for the next level down within which it is interpreted. This hierarchical structure reflects the way we think and categorize things. Embedded in these is often a hierarchy, a membership hierarchy. So you've got animals, dogs, Alsatian, Henry. So within these hierarchical structures, you've got an is-a hierarchy used for classification and understanding. And you've got these in indexes, library systems, enabling understanding by class properties and associated with the expectation. So you've got a bigger class, a smaller class down to the individual members of the class. And this is very important. So that's in an abstract hierarchy, but exactly the same things happen in the physical hierarchy. It underlies a lot of evolutionary development. You have a generic kind of cell, and then you specialize it down to, let's say, a neuron, and then within neurons there are different kinds of neurons, so you specialize it down. Each time you're keeping the generic property, but you're specializing it to give it more and more detailed properties which enable it to do more and more specific tasks. And this is one of the real bases for evolutionary development, because you don't have to develop a new module each time from scratch. You take a module with works, you tweak it a little bit, and it'll do a new job. So you specialize by inheritance with modification, and so you've got cells, neurons, pyramidal neurons as the kind of specialization hierarchy that takes place in evolutionary and development. So inheritance is an important feature of is a hierarchy. It allows an object class to inherit all the properties of its superclass and to add further properties to them. It is a hierarchy, inheritance with variation. And this is how we classify things, it's how biology works, it's how a computer system works. And a lot of my understanding of this came from this wonderful book by Grady Booch about object-oriented programming, which makes this all very explicit. Yeah. So the take-home message here is truly complex systems, physical abstract, are always modular hierarchical systems with class structure and inheritance. You can't create a genuinely complex system that isn't one. Inter alia, this structure allows adaptive selection by modifying parts without disrupting the whole. Now, there are 5 different types of top-down causation. I'm going to call it algorithmic, top-down causation via non-adaptive information control via adaptive selection, with adaptive information control, and with adaptive selection of adaptive goals. And so these are the 5 different types, which are crucially different from each other. They are each top-down. The first one is what I call algorithmic. I've struggled with this name, and this is the best I can come up with at the moment. Its contextual effects determine what happen in the hierarchy by setting constraints for lower-level causation, channeling interactions to reliably get specific higher-level outputs. The initial higher level state is described by a set of higher level variables, then influences the dynamics if the higher level state is changed. The lower level processes and change, and then the consequent higher level outcome changes. And that's what makes it a contextual effect. So one of the simplest is a gas in which you've got a cylinder, and one of the major macro variables for the cylinder is the volume. So you compress the cylinder, you're changing the volume. The root mean square velocity of the molecules changes according to this, and so what you're doing there is you're compressing the cylinder, you're speeding up the molecules, and you are, I think I've got that the wrong way up. It should be the other way up in the last relationship there. What you've got is a top-down effect from the macro scale, the scale of the cylinder, down to the details of the micro levels. Now, at a certain level, that's not very exciting. It's what we expect. But nevertheless, it's a top-down effect. I'm changing a macro variable. Why? Because that's all that I can change. I can't control the different individual modules, but I can change the macro variable. The result is a change in the micro variables. Well, in my book, that's a top-down effect, maybe not top-down causation. Okay, so like I emphasized last time, structures constrain and so channel causal effects. You get reliable behavior arising from carefully designed complex structuring of the chips and very carefully sculpted relationships in the neural networks in the brain. And the micro details are really important here. If you rewire some of those wires, then things may go essentially wrong and you can't coarse grain. And so what happens in the case of the brain, you get a signal going down from the dendrites through the neuron body, through the axons, across the synapse and onto the next one. So the signal travels down, and then what matters is the detailed connection there, and the details of those connections make the difference. And so the point is to describe that details of the connections is a higher level than the level of the electrons traveling down an individual one of those. So you've got a layered structure. You describe the network at this level, and you describe the individual neurons at a lower level. And so it's a higher level actually which determines what happens in the brain, because it determines which cell is connected to which other cell. So in those cases, in these cases, once the connections are set, this is a dynamical system, and it's a predictable dynamical system. You put in an input there, it travels in a predictable way out there and out the other side. Well, it's not quite predictable, because actually there's this statistical stuff which takes place. But nevertheless, It's basically, if we take the artificial neural networks which model this, then once you've set the weights, you've got an artificial neural network with given weights, it's completely predictable what input will lead to what output, and that's why it is an algorithmic system. Now, non-adaptive information control. There are masses of examples of homeostasis in the human body, body temperature, blood pressure, heart rate, transport across membranes. Each is governed by implicit goals embodied in the physical structure of the body, and the human body has thousands of control systems in it. They occur at all levels in the scale, and they've been built into the body through the process of adaptive evolution, and so in a sense embody images of the environment. Now, feedback control, you've got a system state, you've got your goals, you've got a comparator. An error message goes to a controller which changes the state and makes it what you want. And the classic example is the temperature of a shower, where the system state is the water temperature, the goal is what you want it to be, you are the comparator, the controller is the tap, and you adjust it to get what you want. The speed of a steam engine was the original one, the direction of an automobile, and so on. And it involves information. The system state is measured and sends information around the loop to make it happen. Now, the point about this is that this only works if you connect the thing together, and the thermostat I had last time is an example like this. And if you cut one of the wires in the system, all of the components will still be there. Every part of the system will be there, but if you cut the wire whereby the information feeds back, the system won't work. That's why it's an emergent system. And the series of goals in a feedback control system are causally effective. They involve information about the system's desired behavior or responses. Living systems are goal-seeking or teleonomic. These goals are not the same as material states, for they are desired rather than actual states. They will be represented by material states and by systems that will make them causally effective, but the goal itself is not a physical thing. A complete causal description must take these goals into account. They exist as emergent properties. They are not embodied in any component on its own. The nature of causality is quite different when feedback control systems are guided by goals. Us physicists think of physics equations of state initial conditions giving you outcomes. Now, for any specific system, the physics is the same, the equations of the state are the same, so initial conditions give you outcomes. That's the standard physics way of viewing things. For a feedback control system, the same physics, but now the physical structure and the goals give you outcomes. For the system, let's say the thermostat, the physics is the same all the time, the physical structure is the same all the time, but you can change the goal by adjusting the control, and so in fact the goals determine the outcomes. And the whole point of a feedback control system, it's the opposite of the physics one. In the case of a feedback control system, the initial conditions are irrelevant. Okay, it's the goals which determine the outcome, as opposed to the standard physics situation where the initial conditions determine the outcome. So the outcome of a feedback control system is determined by the goals rather than by the initial data. It's a completely different type of causality. In human activity, we have got hierarchy of goals. Our actions are governed by hierarchically structured goals at all structural levels in society. They may be explicit or implicit, qualitative or quantitative. They're not physical quantities. They can be represented in many ways, and so are effectively an equivalence class of representations, well, I'll come to in a minute. But just take any activity, like we're going to bake a cake, so we've got to go and get the ingredients, so we've got to get on a bus and go to the store. There's a hierarchy of things you have to do, each of those involving a series of goals, and then you do them. You tick off those goals one by one, and then in the end you get the cake which you were aiming to get. So that's the second form. The first one was algorithmic, the second one was feedback control, the third is adaptive selection. Adaptive processes take place when many entities interact and variation takes place in the properties of the entities, followed by a selection of preferred entities that are better suited to their environment or context. It doesn't have to take place in the repeated way it does in Darwinian evolution, although that is an extremely important way. It can happen in a once-off case. Higher level environments provide niches that are either favorable or unfavorable to particular kinds of lower level entities. Those variations that are better suited are preserved and the others decay away. And I've given you the example of the polar bear or the black bear last time. A different environment would lead to a different outcome, and hence it's a contextual effect. Now in biology, the evolution, the redevelopment of genetic information is one example. The basic learning process is another example. When we learn something, we go through an adaptive selection process. We make theories of various kinds. We try the theories and then we reject the ones that don't work. We keep the ones that do work. So that's a process of adaptive selection. In computer stock control, choosing what items to order, you have to learn training neural nets, genetic algorithms. Now why did I put choosing what items to order as an example of adaptive selection? Let's strike that one out and keep the other ones, training neural nets and genetic algorithms. There are many others, as George Dyson describes in his book Darwin's Machines. So genetic algorithms are specifically designed to determine optimal solutions by using the analogy with natural selection in biology. Training neural networks, you've got a general neural network, it's not trained to do anything, and then you feed it in a particular patterns you want to recognize, it comes out. Recognizing that pattern, you've adaptively changed the weights in the neural network. Selection is the way meaningful information is created from a jumble of disordered objects. Everything you need to know is there at the bottom. So in this diagram, you start off with a jumble of states. You go through a selection gate with some selection criteria. Disorder goes to order, the ensemble comes to the conclusion particles, and that's how you created something which is much better ordered than below. Everything you need to know is there at the beginning, but it's hidden in the ensemble. You have to select what is relevant. So meaningful information is gained by discarding all the information that is not meaningful. And the classic example here is deleting files or emails on your computer system. They come in and you don't want a lot of them. So there's this jumble of stuff. You keep the ones you want, you get rid of the rest, and you've now got an ordered set of emails or files where you had a mess. Local entropy is decreasing as order increases, and in this process of erasing is a dissipative process according to Landau. So there's, and the nature of causality again is different than when adaptive selection takes place. Whether it's once-off or repetitive, you've got physics, physical structure, and adaptive criteria giving the outcomes. But there's randomness in the ensemble. So the adaptive criteria, they are determining what happens, but not unique outcomes, because there's a randomness in the ensemble which goes in. So the outcome of a selective system is not determined uniquely by the selection criteria or the initial data. There's a kind of a random element that takes place there, particularly as there may be multiple adaptive peaks in the selection landscape, and you may end up on any of them. So in the selective process, you may end up on the top there and get stuck there when you really should be over there and get stuck there. And so adaptive selection could lead to kind of different kinds of outcomes depending what initial data you throw in. Okay, now the next one is adaptive control. So the question here is, when you have a feedback control system, you had a set of goals. Where did the goals come from? For instance, blood pressure. Where did our body get the blood pressure or the temperature, which we've got all of these systems control? And the answer is that came by adaptive selection. Another example is Pavlovian conditioning. In Pavlovian conditioning, a conditioned animal is basically a feedback control system. You do something and it will try to attain the goal which you've told it to do. If you now change the training, so you used to shock it with certain income, you change the conditions, you give it a reward instead of a shock, or vice versa, then the dog will adapt to this new situation. And so Pavlovian conditioning, when you change the conditions, is an example of adaptive control. The dog changes its goals when you do that. Genetically determined goals determine how homeostasis works, blood pressures, body temperatures, and so on. And evolutionary game theory models are a model in computer. And the most important one in some ways from the viewpoint of higher level complexity is adaptive selection of selection criteria. I've emphasized in adaptive selection you've got an environment but you've got selection criteria. Now where did those selection criteria come from? And the answer is again they were in general adaptively selected, not always but in many cases. So choosing criteria for selection by adaptive selection is the higher order thing which determines the start of real intelligence. So an example is selection of spam filter criteria. So you've got a spam filter which is sorting out the stuff you want to let through or not. Someone has to choose the criterion for the spam filter. That's the higher level thing. Chess playing programs, what's the criteria of play in your chess playing program? And that again, the chess playing program is trying to achieve certain goals in an adaptive way, but you can change the goals at a higher level. And in the mind, reflection on purpose, meta-analysis. You're using all your mind, all the time your mind to learn, but you're doing it according to certain goals you've got for the processes of learning. If you change your own goals by a process of thought and meta-analysis, then you have changed your criteria for adaptive selection. And this is usually you have to do in a symbolic way. My own belief is that, in fact, the adaptive selection of selection criteria probably only occurs for intelligent beings. I don't think it can occur in the animal kingdom apart from intelligent beings. So it involves, in general, reasoning about goals based on symbolic representation of issues, purposes, and meaning via language and mathematics. So I think this is where you've hit the level of intelligent top-down causation. So the last three are all examples of complex adaptive systems Murray Gell-Mann wrote about in his book The Quark and the Jaguar. And the crucial point I want to give here is that I've looked at 5 different types: the algorithmic, the feedback control, adaptive selection of goals, and adaptive selection of selection criteria. 5 types. The last 3 are complex adaptive systems. Only adaptive selection creates new information. There are many people trying to do models of the brains based on dynamical systems theory. Now, dynamical systems theory cannot create new information, it cannot learn. There are many models of biological systems based in homeostasis, feedback control systems. By itself, that cannot learn, it cannot create new information. So the fundamental point is that if you're trying to model a biological system which learns, or any system in which new information is generated which wasn't there to start with, you've got to have adaptive selection. And so, as I said many years ago in my inaugural lecture as a professor of applied mathematics, the most powerful tool of an applied mathematician is the wastebasket, where you throw away the theories which don't work. Java, for instance, uses an automatic garbage collector to manage memory in the object lifecycle and get rid of stuff you don't want. What's the criterion you use for getting rid of stuff you don't want? That's what matters. Adaptive selection enables learning. It enables new meaningful information to be collected and stored in memory, and it's not possible in these first 2 cases, dynamical systems and feedback control. And if you look at the current literature, you will find various people trying to develop theories of the brain and biology in which they do it on the basis of dynamical systems or feedback control, and it can't be done. So the take-home message here, there are 5 essentially different types of top-down causation. All 5 occur in the real universe. The last 3 are all examples of adaptive selection, which is the only way to create new information or structure that was not there before. Right. Aristotle's form of causalities. The key point about causality is that simultaneous multiple level causality, interlevel as well as within each level, is always in operation in complex systems. Any attempt to characterize any partial cause as the whole is characterized by that famous phrase, nothing but, as a fundamentally misleading position. Indeed, this is the essence of fundamentalism, which is claiming a partial truth to be the whole truth. But one must acknowledge the whole web of causality to be in operation. There's always multiple levels of explanation that all hold at the same time. There's no simple explanation. So no one one can have top-down explanation as well as bottom-up, both being applicable simultaneously. And so why does an aircraft fly? Now the bottom-up view is you've got the wing and molecules impinging on the bottom and the top, and these are going faster than those because of the shape of the wing. Bernoulli's law lifts it, and that's why the aircraft flies. The top-down view of why the aircraft flies, it was designed to fly. Now that's a highly non-trivial statement. It involved a great deal of money, great number of people, experts in aerodynamics and structures and controls and so on to do that. So the reason an aircraft flies, it was designed to fly, and a brick doesn't fly because it wasn't designed to fly. The same level view of why it's flying is because the pilot's sitting there and he's pushed the throttle open and he's sitting there at the controls and making it fly. And furthermore, he's doing so because there's a timetable which says there'll be a flight from Auckland to Sydney at a particular time of day. And so these are same level reasons as to why it is flying. And the top level reason is because somebody thinks it's going to make a profit for the company. Okay. Now the point about this is that they're all simultaneously true and they're all relevant. It won't fly unless they all apply. So it's no good having the Bernoulli's theorem description for why it flies unless you've had someone design it. So you've got to have all of these to be true. Now this is related to Aristotle's causes, and I'm sure some people here know much more about this than I do. The material cause, the formal cause, the efficient cause, and the final cause. I'm not going to go to the details except to say from my viewpoint the material cause is the lower level physics cause. The formal cause is the same level immediate cause, the efficient cause is the immediate higher cause, and the final cause is the ultimate higher level cause. So I think you can put Aristotle's kind of causations into this framework. There are always multiple kinds of causation at work in any real world situation. In the context of the social world and technological world, they correspond to Aristotle's different kinds of causation. Just because we take most of them for granted does not mean they are not there. Now, crucially important, multiple realization and equivalence classes. The key feature of emergent complexity is that any specific higher level structure can be realized in many ways at each lower level. Equivalence classes of lower level entities correspond to the higher level entity, that is the real causal agent. So here's a case in which I have a higher level state H1. It can be realized at various lower level states H2. Let's think it's the atmosphere of the Earth. Represented on a large scale as seen in a satellite photograph, and at the microscale there can be many different combinations of molecules and clouds which realize it, L1, L2, L3. The lower level dynamics takes that to there, that to there, that to there. When you coarse grain those back to the higher level, they give you different higher level outcomes because it's a chaotic system. And so in that case, the lower level dynamics does not lead to coherent higher level dynamics when the lower level dynamics act on different lower level states corresponding to a single higher level state give new lower level states corresponding to different higher level states. By contrast, if that one can be realized in a whole set of different ways and the lower level dynamics acting on all of them gives you new lower level states that all give you the same new higher level state, then coherent dynamics emerges at the higher level. In all cases, the key idea is that of functional equivalence classes. Each equivalence start is a set of low level states that all correspond to the same higher level state. Like a gas at a given temperature and pressure, there are billions of different ways it can be realized at the lower level. When you coarse grain, all of these lower level states correspond to the same higher level state. Entropy is a measure of how many lower level states correspond to a specific higher level state. And it's the higher level state that gets selected for when adaptation takes place. And it doesn't matter which lower level state realizes the higher level state. The higher level state gets selected, and any one of the lower level states will do for the purpose of higher level adaptation. Whenever you can identify existence of such equivalence classes, that's an indication that top-down causation is taking place. Now, so an example of how this works. Take any folk psychological state law, say if folk psychology 1 gives you folk psychology 2. The causal relation is described by a notion of an if-then statement. The following would be an example of a commonly employed folk psychology law. For any person P, if P desires Q and believes that doing X will achieve Q, then P will do X. ceteris paribus. So that's a kind of a folk psychology law. It's a higher level law at the level of thoughts in the brain. You've got a goal and you think that if you do X, you'll get your goal, then you'll do X. That's a folk psychology law. Now, the problem is that FP1 and FP2 are multiply realizable at lower levels in the brain. In the brains, each of them can be realized in billions and billions of different neural connections and electron flows and so on. And so if you had a bridge law from the lower to the high level, it would look like this. Folk psychology 1 is B1 or B2 or B3 or B4, billions and billions of possibilities. The second one would be billions of possibilities, and you would get the following statement at the low level. This or this or this or this or this will give you this or this or this or this or this. Now, that's not a very useful statement of causality. There are two problems. Neither the antecedent nor the consequent describes a biological type in state B, and the sentence described is not a law of biology. The real causal effect is at the higher level. Here, the real causal effect is at that level, and trying to describe it at the lower level gives you a statement which doesn't actually make sense as a statement at that level. So the take-home message is multiple realization at lower levels is a key aspect of top-down causation. It doesn't matter which lower level instantiation of the high-level structure or function is realized. From the higher level viewpoint, it's all the same, as long as the high level purpose or function is realized. And there's numerous examples in biology. I just need to see. I don't care what kind of eye I get as long as I can see. I don't care what kind of genes I get that allow the eye to come into existence as long as I can see. So the selection is for any gene which will lead to any type of eye which will enable me to see. It's this multiple level cascade. Now, how can it be possible as a physical process, given claims of causal closure of physics at the lower levels? In essence, the argument is wrong. Physics determines what happens at the lower level, but does not account for the higher level kinds of causation that in fact determine what happens, as I've been indicating. And it happens inter alia by changing the level of causation at the lower levels. Physics enables things to happen, but higher levels decide what happens. So the first thing is the functioning according to the laws of physics of the parts of a given nature is often determined by context. High-level purposes can conscript physics to its ends by changing the operating context and altering context-dependent constraints. Structure and boundary conditions affect outcomes. That's the central part. And I've talked about this a lot, so I won't say anymore. Computer operated as a music system or word processor, muscle cells, and so on. The lower levels are the same in both cases. The higher level is setting the context, deciding what happens. Causal openness is there because it can often, the higher levels can often change the nature of the parts. We don't just have invariantly functioning parts assembled in different ways and so operating in different contexts. The nature of the parts, the way they function, is also affected by context in a top-down way. Indeed, the parts are often adapted to their higher level functions. So hydrogen atom in a water molecule is not the same as a free hydrogen atom. The very nature of the entity at the bottom has changed. So you don't have, the model we've got is these rigid billiard balls bouncing into each other which are unaffected by the context, but that's not what happens often. Free neutrons decay in a period of 11 minutes, bind a neutron into a nucleus, and it's stable for billions of years, and otherwise we wouldn't exist. So context changes the nature of the behavior of a neutron, and that's very, very good for us, or we wouldn't be here. Crucial, cells in the human body, through developmental biology, each cell in our body starts off pluripotent, and it then specializes. Some specialize to be bone, some to be blood, some to be neurons, and so on. And so the cells in the body, they start off being generic ones, but then top-down action in the developmental processes tell the cells what to be. I'm talking in a figurative kind of way. And they then become adapted to the purpose which they have to function. And so then things become neurons, which could have become blood or they could have become bone. And so the top-down context changes the nature of the bottom-level elements. Sometimes the lower-level cases create the high-level context creates lower-level entities. In many cases, the lower entities wouldn't even exist without the higher-level structure. The higher-level structure makes their existence possible. An emergence of high-level entities has clearly occurred when lower-level entities cannot exist outside their higher-level context. In physics, the possibility of existence of phonons is a result of the physical structure of specific materials. The structure is at a higher level than that of the electrons. In biology, symbiosis, pairs of animals that cannot exist on their own. If they cannot exist of their own, then of course you can't even begin to say the thing emerges in a bottom-up way, because the parts on their own simply cannot exist on their own in that case. And for instance, in the human body, we've got 10 to the 13th cells. You take those cells out and have it sitting there on its own, it won't survive for more than a minute. And then top-down action can delete lower-level entities. I've talked about this. There isn't a fixed set of lower-level entities when adaptive selection creates order out of disorder by deleting unwanted lower-level entities or states. Top-down action selects what the lower-level elements will be. In physics, an example is state vector preparation. In quantum physics, in biology, Darwinian selection. In the brain, vision and attention, where we ignore everything that is background in order to pay attention to what happens. Billions of bits of information enter our eyes, and the brain throws away almost all of them and only pays attention to a very small fraction of them. And so you delete lower-level entities and only look at the ones that you want. And then finally, chance. Statistics associated with coarse graining, random boundary conditions, quantum uncertainty means physical outcomes is not uniquely determined by physical effects alone. In complex systems, this unpredictable variability can result in an ensemble of lower-level states from which a preferred outcome is selected according to higher-level selection criteria. And it's the higher-level selection criteria which shapes what happens. And in fact, you need randomness in biology for biology to work. If you didn't have the randomness, you couldn't have adaptive selection. This provides the openness needed for adaptive selection processes to choose outcomes that satisfy higher-level goals and values. Thus, top-down selection leading to increased complexity is enabled by the randomness of lower-level processes. An example is adaptive immune system. Another example is nanotechnology selection of desired projects. So the take-home message here, top-down causation is possible not only because the high-level structure provides a context, but it often alters the nature of the lower-level elements. It may even create or delete them. And this way, lower-level elements are often specifically adapted to their higher-level functions. Okay, the final thing is why the argument against it from supervenience fails. Supposing one could reproduce in every detail the structure of a computer or a brain and its current state of excitation, would the identical higher-level behavior or effects emerge? If I could duplicate a brain, every detail, including all the excitations, would that determine higher-level behavior? And the answer is yes, maybe. I'm willing to accept maybe. So the higher level behavior is determined in a bottom-up way by the lower levels, and that's the argument from supervenience. Thus, the brain works out the effects of Maxwell's equation in a bottom-up way because it's got the structure, it's got the excitations, it's all ready to do it, and there's no need for top-down effects to occur. That's the argument there. But you can't get to that initial state in a purely bottom-up way. The brain or computer can't self-assemble in a bottom-up way. How did the electrons in the brain know about Maxwell's equations? They are there in a context of neural connections that have been taught about those equations through a social process of education. So the wiring in the brain which knows about Maxwell's equations has come about through a process of top-down causation. It's only when you've reached that state that the bottom-up thing can take place. So you can't get the final result without top-down causation, even if the final step is purely bottom-up. Now, Douglas Campbell. Should I use the word realisation, not causation? And I got this very useful email. The term top-down causation seems dangerously misleading to me. It suggests that entities at the lower level are not able to determine what will happen by themselves, that the micro-level story is not causally closed, and that the higher-level things are somehow getting in and actively making things happen at the micro-level in a way that could not be explained and predicted in terms of micro-levels only. But in your examples, the micro-level is causally closed. E.g., you can in principle predict exactly what the computer will do at the micro-level by considering only its wiring diagram and voltage levels, without taking high levels consideration into account at all. Similarly, presumably for the thermostat, albeit in this case the calculation will be intractable in practice if you try to predict everything at the level of atoms. So this is the supervenience gambit. Okay. He carries on. Causation is a relation involving two events at different times. So the key thing what he's pointing out is causation, you do thing now and the effect occurs later. Realization is a relation involving two things or collection of things which exist at the same time, but on different scales or explanatory levels. So a natural way to describe the phenomenon you listed is to say there's a vertical relation or realization between entities at different levels, with the lower level entities realizing the higher level entities, and parallel layers of horizontal causation at each level. There's no bottom-up or top-down causation. All the levels of causal explanation are equally valid and real. They complement each other, they don't complete. I think that's a wonderful description of what might be the case. And I agree completely with that, with one proviso, which I will come to. And so I should have talked last time about the horizontal and vertical levels of structure, which I didn't do, but it is in the book actually. But in fact, this is a wonderful description of that, the way that that can work. So thank you very, very much for that. It's very, very helpful. E.g., lots of atoms are bounded together to form the lever of the thermostat. We can say that the movement of lever causes the air to warm, or that the movement of the giant constellation of atoms that composes the lever causes the atoms that compose the air to move faster. These are parallel and complementary causal stories at different levels of explanation. The latter story abstracts away from the mind-bogglingly complex details of the former story and is much more tractable for the human mind. Also, the latter story could remain true even if the former story was somewhat different, e.g. because the lever was slightly different shape. The latter story is in this respect more general. The entities as posits are multiply realizable, and this takes me back to the argument I gave just a minute ago. E.g., the behavior of the computer is completely predictable based on the knowledge of only of its wiring diagram and its starting state, which encoded in its input voltages. It is also completely predictable based on the input that is given to some virtual machine it is simulating. Again, the lower level causal story and higher level causal story complement each other. The computer realizes the virtual machine in virtue of how its wiring has been engineered and in virtue of the input voltages it has been given. Of course, if one wants an explanation as to why it's been given these input voltages and other voltages instead, then we need to look to the intentions of the program or the neurons of the programmer at the lower level. And so you end up carrying on in that. So this is a very, very helpful and useful input, and may to some extent fix the problems we were having at the end of last time, where people were querying my use of the word causation. Just out of interest, in the neurobiology literature, the word used is modulation, top-down modulation, bridging selective attention, working memory, and there's lots of papers in the neuroscience literature which use top-down modulation as a word. I don't know if you like the word modulation rather than realization. So the revised picture is here. We've got our horizontal levels. At each level there's rules, algorithms and data. Causation level 3, causation level 2, causation level 1 and causation level 0. Emergence, the higher levels emerge. Realization, the higher levels act down. Causation is same level. Emergence is upward and realization is downward. So that's the kind of picture that we're getting. And for my purposes, this does most of what I want. It says that the top-down effects occur. It says every level is real, which is exactly what causation can be considered as any of those levels. This agrees with Dennis Lobel. It says emergence is real. This is, in effect, an argument for strong emergence. I think this is an argument for strong emergence, and I think it's a very nice argument. The final question is, do I believe it fully? So the question I would ask you, in that downward process, you were looking at the case when it happens instantaneously, but sometimes there are delays in when it happens. So when is the realization also causation? It's not also causation for synchronic emergence. That is, when you enter and run the data on a computer program, I think that's correct. Everything is happening at the same time, and you can talk of it at any level, but actually it's all happening at once. Running the lower level, higher level processes is the same as running the lower level processes, which are realizations of the higher level. They happen simultaneously. But realization may be causation for diachronic emergence. That is, when developmental processes and evolutionary processes, because those are not instantaneous processes. In the cases that Dennis Noble writes about, the heart sends signals down to the genes, to the genetic level, that starts the signal. The gene regulation network starts the genes to create proteins which then alter what's happening at the lower level, and there is a delay there. So there is in fact a causal delay in that kind of case. In the case of evolutionary processes, you get a variation, and then you try it out against some criteria, and then the selection takes place after the creation process is taking place, and so there's a time lag there. So I very much like that previous description, but and I think that can be used in all cases, but I think in some cases I may also actually be able to attach the word causation. Possibly. It's a subject for debate, but it's a very, very interesting and a very good debate. So the big picture, the nature of causation, the view is that higher levels are causally real because they have demonstrable causal powers over the lower levels. That's the word I used before. We can argue about that. Indeed, the issue of ontology is clear at all higher levels. It's only at the lowest levels, where quantum effects dominate, that it gets murky. I suggest top-down effects from the higher levels is the key to the rise of genuine complexity, such as computers and human beings. And the hypothesis is that bottom-up emergence by itself is strictly limited in terms of the complexity it can give rise to. Emergence of genuine complexity is characterized by a reversal of information flow from the bottom up to the top down. For the reasons I've said, an animal has to adapt to an environment. That means information must flow from the environment into the animal to alter its structure or its behavior, or both. And I'm using the word flow in a kind of analogic way, but I mean through the standard processes of Darwinian selection. So at no point am I suggesting that the laws of physics are violated. That is not what I'm suggesting. I'm suggesting, as Robert Bishop puts it, that the physics makes things happen, but the higher levels in many cases decide what it is which will happen. Thank you.